This video is a huge video because it's gonna talk about a lot of stuff, alright? And I may have a certain careless mistake somewhere. So yeah, stay on. Alright, we have a question. Alright, the cylinder pipe have blah 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 blah. Alright? And the pipe blah 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 blah. But I just want you to know that we are required to find the shear stress, and we're required to find the axial and hoop stress, and then form a complete stress matrix. Then find the principal stress and the vorticity stress. So we have 1, 2, total of 5 stuff to find. Alright, so let's start. So this fella actually calls us to find our shear stress first. So let's just find our shear stress. So this shear stress is actually this one. And just take note that the outer radius is r. Okay, and let's just start off with how the question is being so-called set up. We have an inner radius. Alright, this is the inner radius over here. This one, alright, is 25 mm. Alright, while this one, the outer radius, alright, r, is actually some values, alright, plus the thickness actually. Alright, so it's 5 mm. The thickness over here is 5 mm. Okay, and it's pressurized with gas. So this cylindrical pipe is pressurized. So it's not talking about being kinda pressurized. It's talking about within it itself is pressurized with a gas within itself. Alright, so it's within it. So we can say that it's PI, right, inside, interior. And we assume that the exterior pressure is equals to 0. Alright, this is always the case. Right, and this is a very powerful assumption, in terms of something that we should know. Alright, after knowing all this, let's just start off. We just simply sub in all the stuff. Alright, we know what is T. T is the torque that is given. Alright, 12 kilonewton. Okay, actually the shaft itself. Alright, hold on. So this shaft actually experiences a certain torque. Alright, it's being twisted. So it's trying to so-called bend it. So it become like that. I don't know how I'm drawing, but yeah, looks like something else. But anyway, let's just sub in the stuff. Alright, we will know that shear stress is equals to this. So I'll just write step 1 is equals to our torque is given 12,000 Newton meter. Alright, because it's 12 kilonewton. Alright, multiply by r. So we don't know what is r, right? R is actually the outer radius, as we have said earlier, the outer radius. So we know the inner radius 25 mm. So the outer is simply 25 plus 5, because it's the inner plus the thickness. If you still remember, this is the inner plus the thickness, you'll get your outer radius. Alright, so I'm just simply doing that right now. So I have 30 millimeter. Right, so if you want to convert to meter, because everything is a meter, so it's like multiply with 30 divided by 1000. Millimeter to meter is 1000. So I have this thing over here. Okay, then I got this huge chunk of stuff. So it's R4. R4 is what we have found out earlier. 30 divided by 1000 our outside radius, and our inner radius is this one. And half pi, I think you know what is pi, 3.14. So just find for this J now. Okay, so when I do this, so instead of skipping, I'll just go through with you with a certain cheat code that I think might be fairly useful. Is that 30 divided by 1000 is really a very small number, and then if you quote to the power of 4 is a really small number, you're gonna minus a very very small number, things gonna get very very hairy. So what I thought is to summarize this as 10 to the power of what? 10 to the power of 3, right? 10 to the power of 3 is 1000, right? And then if you multiply in into this 4, what you have is 30 to the power of 4, and then I cancel already. So this thing to the power of 4 is 10 to the power of 7. Alright, so actually this one also cancel, and then this one also can be cancelled, and this thing is also 10 to the power of 7. Alright, then I can just simply factorize out 1 divided by 10 over 7 from them. Alright, because it's already within it. So what I have this things over here. Okay, I just clean things up a little bit. So what you left is only 30 to the power of 4 minus 25 to the power of 4. And we just simply type in calculator with an easier form of calculator typing. Alright, what you have is, and in fact I have a understanding mistake. Alright, I just now say that I factorize out this 1000, right, because it becomes 1 over 10 to the power of 3, right? So 1 to the power of 10 of 3 to the power of 4 is actually 10 to the power of 3 times 4. Alright, so we will have 10 to the power of 12, not plus. Alright, not plus. Okay, this is something that I need to take note of. Alright, so it's 10 to the power of 3 and to the power of 4. Alright, unless you're taking 10 to the power of 3 times 10 to the power of 4, then it's another scenario. We will have this one. But it's 10 to the power of 3 to the power of 4. This means you're gonna multiply. Okay, I actually forgot this important mistake. So let me change. Alright, 12. And then 1 over 10 to the power of 12 is actually 1 minus 12. Alright, this, yeah. Okay, I'll also cancel over here. So after that, once you sub it in, it's quite straightforward already, and then you just and remember this is actually half pi, it's not 1 over 2 pi. Okay, be very careful. And then yeah, this is it, and then I'll just simply sub it in over here. This is our stress force, right? Our stress, shear stress, sorry. This one cancel because 1000. Alright, so now what we have back is 546.45 MPa. Alright, in terms of megapascal. This is because this Newton meter. Alright, and then this is this below one is actually what it is. This whole polar thing is actually meter also. Alright, so in this meter cancel, so we are left with Newton meter, which is Pascal. Alright, but because it's in terms of a 10 times power of 6, so we write as mega. So we have megapascal over here. And this values actually differ from what we have in the class, maybe 54.645. I don't know why 54.645. Maybe I have some misunderstanding somewhere. I don't know. But I'll just take it as this first and see how it goes. Alright. Also another careless mistake is that this is 30 over 1000 is meter, right? Meter to the power of 4 is actually meter 4. Alright. So when I sub in over here, I should sub in instead of meter, it should be meter 4. So when I cancel, I'll become meter 3, meter cube. And when I cancel with this one, I have meter square. So Newton per meter square is equals to Pascal, because it's the amount of force on a certain area will give you a certain stress, if you still remember. So therefore, this is something that I actually careless mistake of. But just take note of it. Alright. But still, the numbers, I keep on calculating. I don't know why I still get back this one. I don't know. Seriously, I leave you to think about it. Therefore, we have our shear stress as 546.45 MPa. Okay? Alright, next up is to assume that your pipe is a thin wall. Alright? And therefore, find your axial and hoop stress. And therefore, your axial is actually your longitudinal one. Alright? Your sigma ZZ. The right axial is because it's easier to write, because it's compared to longitudinal, it's a lot of alphabet. This one is axial, it's just 5 alphabet. But anyway, just take note that axial is actually longitudinal. Right? Since we know that, then, and therefore when we reach here, the first thing we ask ourselves is that what is the radius that we're going to use? Is it the inner radius or the outer radius? Okay, in fact I also don't know how to explain, but to a certain extent, you can use both of it and then see that which is the highest one, you just use that one, because you often want to estimate the highest stress, so that is the worst case scenario, I think. I may be wrong over here right now. Right. But anyway, as you can see, this is the one that we have done before, and the results aren't very much significant. There will be a little, the percentage is just 2% difference only, or 3%, and so on and so forth. So we should be fine for our case. So so therefore for me, I'll just take in terms of the outer radius. Alright, and the pressure itself, it's, if you were to take a look, it's a 300 bar. So this plate is at 300 bar. But however, because we want to talk in terms of this is 10 to the power of 5, right? 1 bar is 1 times 10 to the power of 5. So I'll just write it over here first. Right, while our radius is outer radius is 30 divided by 1000. Okay, divided by the thickness. Alright, it's what is it? 5 divided by 1000. Alright, what I have is calculate. You can simply cancel off this one. Alright, because this 1000 in the end will be coming out to here 1000. Alright, if you were to do some math, alright, just do it. So therefore when you type in the calculator, it's easier to type. Alright, what I have is actually 180 megapascal, meaning it's times 10 to the power of 6, so it's a huge number. Okay, and therefore since this is divided by t over here, and then this is divided by 2t, so the difference is actually, if let's say this one divided by 2 will give you your sigma zz. Alright, so therefore I'm just taking 180 divided by 2, I'll get 90 MPa. Alright, it's because sigma theta theta is equals to PR naught t. Alright, and then our sigma zz is PR naught over 2t, or in other words, half of this sigma theta theta. Alright, I think this is better way to express what I'm doing right now. Alright, 180 times half. Alright, so that's why I'm having 90 MPa over here. Okay, and therefore this is my axial stress, this is my hoop stress. Okay, so and write down the complete stress matrix. So we have a shear stress now, and then we know our stuff over here, and then this complete stress. Now we're gonna complete the stress. So I'll have sigma 1, right? Sigma should I have sigma 1 what is it okay, sigma 1 1, sigma 2 2, 0. This is in fact your what am I doing? Sigma theta theta and sigma zz is your axial and hoop stress, is over here. Okay, where sigma theta theta you know is straight away largest number, so I put it over here. This must be the largest, this must be the smallest. Alright, and add with the shear stress that we have found earlier. Alright, shear stress, there will be no normal stresses because the normal stresses is here and here, right? But we are turning here and here only. Alright, so the normal stresses are in fact 0. So we know that our shear stress, alright, is a very huge shear stress, 546.45. Okay, so I'll just write it down, 546.5 for simplicity's sake. Alright, and this is in fact we call this sigma theta z. It's a shear stress between the hoop stress and the axial stress. Alright, what it means is that this raises a question. Alright, we know that sigma, if you have a cylinder over here, you take a piece of this cube, alright, and just translate it over here. This is your sigma zz, this is your sigma theta theta, right? Now sigma theta theta actually goes in a loop, alright, which is also the same path as the torque, the shear stress. But why that we actually split them into two systems? Maybe I think you're just analyzed in terms of the pressure, in terms of the thin wall analysis, and therefore it's in terms of all this. The thin wall, because if you remember, the thin wall is in terms of hydrostatic. Alright, we talk about it. Alright, so hydrostatic is all in terms of it's not exactly hydrostatic, but rather than because you have a certain object over here within, and then you are applying certain because they are actually targeted with a certain pressure, right? You have this cylinder within it, and the pressure is actually acting all against these surfaces. Alright, so these are all the normal stresses that is from the fluid. So the fluid I mean FLUID, the fluid forces is always acting perpendicular to the plane, so therefore it's the hydrostatic force, and therefore we are talking in two different stuff, and therefore this, although this is in the same direction, but the torque itself is the torque because it's trying to twist the exterior part, while the so-called this particular radial stress is actually trying to actually so-called, in some sense, because to rip this apart, alright, to actually rip this apart, because the radial stress can move in two directions if you still remember, alright, sigma theta theta. So this is not exactly shear stress, but rather than it's a force trying to rip off this piece, trying to create a crack along this line. So the radial stress is that manner, and the longitudinal stress is actually trying to create cracks over in the longitudinal line. Alright, I may be wrong in my explanation, but at least something fairly useful to discuss. Alright, we know our sigma theta theta is 180, this is 90, because this is what we have found just now. Alright, so I'll just simply add them up together because they're just themselves. Alright, so what I have is this, and they are MPa. Okay, as you can see, the shear stress comparatively to the hoop stress is actually quite big, quite huge. So therefore, I don't know whether am I right or wrong, but it may be the case because is the hoop stress and the axial stress are just something within the system itself, and then exteriorly is the shear stress that is trying to do stuff. So I don't know, leave you to think about it also. Alright, so we have a complete stress matrix over here. Okay, next we're gonna find the principal stress. Alright, principal stress is straightforward, and this is my 2D invariance and its own general formulas. Alright, something that is slightly different from what you have over here or here. These are all 3D, right? These are all 3Ds. So we're just now doing 2D's equation. Alright, and therefore let's just sub it in. Alright, this is our sigma 1 1 2 2 1 2, sigma 2 2, and sigma 2 1. Alright, just simply sub in sigma 1 plus sigma 2 2. So what I have is 180 plus 90, 270. Alright, and then the rest you can calculate yourself. And we have 205.79 or 64.2. Alright, this is the calculation, alright, for when 546.5 is not calculated. Alright, it's 54.65. Alright, so therefore we have proved to ourselves that our calculation for all the way back from the very previous part for the shear stress, this should be 54.65. Alright, but I don't know why. I don't know what's wrong with my calculation for some weird reasons. I think now I'll just cancel all the stresses as 54.65, our shear stresses. But what we have is these two values. Alright, what we have is these two values, and therefore the higher one is 205. So I'll just write it down. Principal stress. Alright, 205.79 and 64.2. Sigma 1 and sigma 2. Our principal stress has no shear stress, if you still remember. So this is our principal stress. If it's in terms of 3 principal stresses, alright, then I'll just write it in terms of 205.79, 62, sorry, not 62, 64.2, and 0. Okay, and the rest are zeros. So this is the one that we have written over here. Over here, I'll just simply write it in 3 times 3, where the rest is simply zeros. Maybe I should write properly. Hold on. And take note that this is not 62, this is sigma 2. Alright, it's the principal stress, or the second one. Alright, so this is our 3D principal stress. And you may wonder why just now I say that I change it to the shear stress, I change it to 54.65. Alright, it's because after I solve for our roots over here, alright, I realized that my values for my principal stress are all imaginary. Alright, real and imaginary, which is weird. So therefore I think that 54.65 is actually the correct one. But now since we have the principal stress, our last job is to solve for our von Mises stress. Alright, our von Mises stress. How? So this is our von Mises stress equation. Alright, so this is sigma 1, this is sigma 2, this is sigma 3. Alright, this is the smallest value compared to the other two, and it makes sense also, right? So that's why 0 over here is a legit number if you still question yourself. And this is our principal stress if you still remember. So just simply sub in our sigma 1, sigma 2, and sigma 3. Alright, it's just subbings. Alright, what I have is, so we have all this, just sub in over here, and then this portion over here is this value. Well, I have 182.4 MPa, and our von Mises stress is actually lower than our the highest stress that we have. Alright, because we have so-called 2D system, I would say. Anyway, so this also proves that not all the normal stress are 0 that causes the von Mises stress to go larger than this. Alright, this hypothesis is wrong. Anyway, this is correct value, but in terms of this, if previous video we say that if one of the normal stresses is 0, the von Mises stress has a potential to be larger than this one. Alright, but looking in another perspective, we are just looking in terms of a 2D system. Alright, if you still remember, a thin wall is a 2D system. Alright, because it's only talking about the sigma zz and the sigma theta theta. Alright, while the radial stress is actually 0. So therefore we are actually talking about 2D system. Anyway, let's just stop here, and then in the next video talk about question 5. I shall see you there.